about IR transmitter receiver implementation on our DE1 Terasic board. So as you can see, when we're doing IR transmitter and receiver, you'll need a transmitter and a receiver module, and to tie both of those, you need a top module which ties both of these together. And this 7 segment display, we use this because we're gonna display the data that the IR receiver is receiving using the 7 segment display. So as I mentioned it in my earlier videos, a 7 segment display on a Terasic DE1 Terasic board is basically an active low, which means that whenever you have a zero, that bit will be lit up. So yeah, accordingly we have coded our data in hex. So which means that each of those 7 segment display can display 4 bits essentially. So 0 to 15, so 0000 to 4 ones, so that would be 15. This is what you could display on each of the 7 segment display, and we have 6 of those. So yeah, this will come in handy later on as we look deeper into the program. So this is our top module. These are D1 SoC board description. As you could see, this basically has the input and output definitions of all the hardware blocks that are available on the FPGA board. You can see DRAM clock, there's an I2C, GPIOs, the 7 segment display. As you can see, it's pretty much all the hardware that you can find on the FPGA board. This is basically a definition of all the hardware that is being, input and output ports of the hardware that is on our FPGA board. So let's dive into the program. This is our negative reset, which means that if it's an active low reset, if it's at 0, the reset is held. If it's at 1, then the reset is not being used. So basically this module will run forever. And this is assign LDR to switches. This basically is it's a sanity check to know to verify whether all the LEDs on our FPGA board are working. So here is our main program. So this wire data is a flag, and this hex data is actually the data we are transmitting and receiving through IR. So as you can see, we have the IR receiver module here. So we basically mapped this inputs to the definitions on our module in IR receiver. So it has a clock, 50 megahertz clock, and a reset, active low reset, and it's been kept at 1. So basically it will keep working forever. And IRDA, this basically this is a flag which shows that the transmission is the reception of the data is still going through. And once your data is received successfully and verified, you get this data ready flag which shows that the data transfer has been successful, and this will be your data. So as I said, we'll be sending the data to the transmitter will be a 32-bit data. Now this is according to the NEC protocol, which shows that the the first 8 bits should be addressed, and then it should have the inverted address bits, then comes the data bits, and then comes the inverted data bits. This is the 32 bits. And as I said, since we have coded from 0 to 15, which means that each 7 segment display can display 4 bits of data, and we have 32. So we'll need 8 LED segments, which we don't have. Since we only have 6, we'll be displaying 24 bits of data. So which means that we'll be displaying this data, address bit, and the inverted data bits. So this is what we'll be displaying on our 7 segment display. So yeah, as you can see, 4 bits are being coded to each of the 7 segment display. Now let's see how it's going to work. So this is a test data which basically receives the data, and this is a data send register and a wire for transmission busy. So what it works is, if a key on our FPGA board is pressed, it resets and sends a test data to check if the transmission is actually working. Data send here is kept 0 because this is just, since this is a test, you don't actually need to send it out. So yeah, data is held 0. And if transmission busy, if the transmission is zero, transmission busy flag is zero, which means that transmission is not happening. This is basically a, an indicator for transmitter to start sending data, and this will get activated once a, data transmission has been done, and this turns into zero. So this is to send the next data over. That's why we have the test data plus one. So basically it sends out the next data to be sent out, else we'll have that data sent to be zero. And this, as I said, this will be the transmitter module. This will have the, it will generate the address and the data bits, and this is again another flag when data is being sent or successfully sent. And yeah, these are few of the other things. Now let's get into the receiver module. This is the IR receiver module, and this basically works on an FSM or finite state machines. There are three state machines. As you can see, there are three states: idle, guidance, and data read. So as you can see, these are being defined here. Now these are some of the parameters which are being defined for state transitions. Let's go through these. Ideal high duration. So when you are in data read and you want to switch to idle mode, if that you know the high is for more than 5.24 millisecond, then the state will turn into a idle state from data read to idle. And same goes with this guide load duration. If the data is low for more than or equal to 4.6, then ideal will go to guidance state. And guidance, if it's the signal is high for more than 4.2, then the subsequent transitions will go on. So this is basically when the data reception happens, and these are the other information. Now as you can see, how would we read our data if it's a 0 or a 1? How would it decode? So here is the idea for that. You can see it will be sampled for every 0.83 millisecond, and within that, if it has a high for 0.52 milliseconds, it will be read as a 0. And if it has it no if the high is for more than 0.83 seconds, it will basically be a 1. So that is the idea here. So how this works is, basically first you wait or watch out for the first 9 milliseconds of the duration. That's when you are in the ideal state. And after 9 milliseconds of low, and when you go to a 4.5 milliseconds of high, that's when you go to guidance state. And further you go to data read state, and so on. That's how your machine works. So here is the functioning of the whole transmitter. So what happens is, there'll be a counter which basically counts. As you can see, there is a counter for every state, that is for idle, guidance, and the data reception state, or data reading state. So yeah, each of those data will be sampled, as each of those bits will be sampled through a series of a counter. So that is the idea with this. And having received those 32 bits of data, a signal will be sent out saying data ready, having confirmed through the NEC protocol, backtracking, and having known the encoding is correct. So yeah, having verified that, the data received flag will be sent made high. So it basically shows that we have successfully received the data. That is basically the gist of how it works. So receiver will have three states called as ideal, guidance, and data read. Guidance is for waiting. Guidance is to basically transition into data read, and the data read is where you receive the bit, sample it, and check for the high duration for zeros and ones, and then subsequently store it into a register. So that is how the IR receiver works. Now let's jump into the transmitter. So yeah, it takes the address and command byte and builds the 32-bit frame, so that it's responsible for building the 32-bit frame. And so as I said, when we are sending or when we are using infrared transmitter or receiver, we basically flash the lights, which means that we are encoding the data that we want to send in a carrier wave. So yeah, or modulating a carrier wave, which means that that carrier wave is basically a means of transport for our data. So having said that, you need the frequency for a carrier wave, right? That's why we have the clock 38K. Basically, it derives from the main clock that we have on the Terasic board, and it generates a 38, 38 megahertz, 38 kilohertz of, you know, carrier wave, which will be, utilized for sending the data. So when the I send is 1, you basically start sending out data and it flashes red. The IR transmitter will start flashing the data. Uh, this is how it starts sending out data. And as you know, for as I explained in receiver, if it's a 0, then it will be high for a shorter amount of time, and if it's a 1, it will be high for a longer duration. That's how you differentiate between 0 and 1. So when the transmission is also being done, there will be a busy flag which shows that the transmission is going on and that it shouldn't be interrupted. So that's the idea with this 3 modules or the 4 modules, as you can see. And yeah, I've gone ahead and compiled this whole thing. Let us now look at the report, post report, and see the resource utilization. So as you can see, ALNs are 183. Basically, initially it was 200, and then after logic optimization and other things, it could be reduced to 183. So yeah, ALUTs used are 305. As you can see, the different values of input functions being used, and then we have the logic registers, the dedicated logic registers, 275 of them being used, and now we have the pins, 241 pins, and then as you can see, none of these hard process systems are being used, and this is the SRAM data which or SRAM storage that is not being used here on board RAM, and we are not using any DSP blocks. We are using one global block, no DLLs or no PLLs. So that is the idea with the resource utilization. Now let's look at the timing report. As you can see, I've already generated 5 longer paths. Let me show you. It has a positive slack, so that is definitely good. And as you can see, the restricted Fmax is 160 megahertz. Now let us go back and look at 5 of the critical paths that we can see. As you can see here, we have listed 5 paths, and you can see how the data is arriving earlier and it's needed at this point, but it's arriving here. So it's the extra slack or the extra time that we have because of our clock and how optimized our design is. So we could further, what we could do is we could go ahead and look it into on a chip planner. But before doing that, let us also look at how it would look, how our design looks while being implemented. As you can see, since I've compiled my top module, it shows all the pins and is the receiver module 7 segment display that we are using, 7 segment display receiver. So yeah, as you can see, all the inputs and outputs being mapped. So yeah, this is a post-fitting view of the cell. Now let's also look at the RTL view. Here is a simpler RTL view to look at the design and understand what is the code that we have written. As you can see, there's a transmitter, receiver, and the received data is being sent to the hex display, to display the data. And these are the register blocks. where we are saving data, and henceforth, as I've explained it in the during explanation of the main module. Now, as I was saying, let's go back to getting through this timing diagram. So as you can see, I have multiple paths here, and I could go and get the report for all of these. So yeah, as you can see, it has a positive flag. Now let us go ahead and try to do or try to move one of the blocks and see what goes on. So let us locate this path on our chip. So yeah, as you can see, our our functionality or our IR receiver transmitter project or the block is being implemented in these parts of our FPGA, and here is the critical path that I marked, or the 5 critical paths that I took. Now what I could do is, as you can see, the cells here are being utilized, or how it's been mapped and how it's been utilized. You could see that. Let's select this cell. You can see, you could clearly see how it's being utilized. Now the other advantage of this is, in chip planner, we could basically move our cells anywhere we want. So what I'm going to do now here is, I'm going to go ahead and move the cell to one of these blocks here. As you can see, the block is moved, and let me confirm this change and run it through. As you can see, I was successfully able to place that or move that subsequent block. Now let us look into the, yeah. As you can see, the entire block has subsequently moved, and you can see it being changed. Now let us move another cell to the other corner. As you can see, we have reached the top. Let me just move to these cells here. As you can see, this is the second cell. Now let me just confirm this so that it could run. So as you could see, I was successfully able to do this second movement. So let us go verify the same. So as you could see, our block is placed at the top here, and one of the other blocks is placed at our very bottom. So yeah, as you can see, the moment is also being tracked here. The old value was the old value of one of the cells was that was placed here, and that being transferred here has changed its value, and the other cell I chose here is moved to the top, and that is what this value is. Now let's go ahead and reopen the timing analyzer to see what actually how it actually affects when I move one of the blocks that are in the critical path. So let me just go ahead. As you can see, it still says we have a positive slack. Let me just look at that. Let us look at the 5 paths that it could show. As you can see, the delay has increased, which is expected to see because we basically moved our critical path to either corners. Basically, 2 important blocks to either corners. Basically, you could say at the either corners of our FPGA. So because of that, we have a lot of data delay. So yeah, that shows that this chip planner basically gives you the flexibility to move the cells around so that you could create more optimized designs and fix it yourself. So yeah, this is the idea. Now let us go ahead and dump the same program onto our FPGA. Now while dumping this, I'll be using the .bat or .bat file, which is a .bat file, which is basically a Windows batch script. You could, instead of opening it in quarters as we were doing before, you could basically run that, and that directly checks if the JTAG matches and the kind of board we are using and the file, the .sof file. So let me show you how that would work. Yes, as you can see, these are my files here. Let me go towards the output files, and as you can see, this is the Windows batch file. As you can see here, you can see that it just it finds the JTAG, basically the blaster cable that we have, the hardware, and then we have the file, the SOF file that we the bitstream generated. So yeah, this is a direct command. As you can see, it's been successfully.
As we can see, I have successfully implemented the program here, and just like I explained in the program, this was sanity check. I have assigned the pins switches to the LEDs. You can see as I turn it on, it's turning on, so that there is a sanity check. Now here, as I said, here is the key 0, which is coded to basically reset or send data, test data. That is what it will be doing. So as I change it, you can see the data changes. This is, we have the IR transmitter and emitter here. With every click, as I said, for every click it sends the test data, and once the test data is sent, the transmitter is not busy, so basically it says it's ready to transmit, and since the receiver is not busy, so it will be ready to take the data. So with every touch, you can see the data. Show the working on the board. As you can see, the light blinking here. So every time I press this, our data is transmitted and it is received here. And as you can see, these values are being displayed on the FPGA board. Thank you.